Good morning, friend. Myself, Dr. Atul Nagpure, Assistant Professor, and I welcome all of you to my Chemistry YouTube channel. Today, our topic is effective atomic number. In the last video, we have seen the Sedgwick electronic theory and the effective atomic number concept, which is also known as noble gas rule given by scientist Sedgwick. He suggested that when any metal ion form a complex with the given ligand, it wanted to achieve the stable electronic configuration of the next noble gas. So in this video, we will try to understand what are the different aspects of the effective atomic number. Now let's start discussion. Effective atomic number is actually can be given by this equation. EAN is equal to Z minus N plus 2 into Cn. In this equation, Z is atomic number of the metal, N is oxidation state of the metal, and Cn is a coordination number of that metal in the particular complex. So you might have realized here, if you wanted to find out the correct EAN of the complex, you must know the exact value of Z of the metal and oxidation state of the metal along with its coordination number. For that, you can prepare one table of various ligands in which we can classify neutral ligand, anion ligand, and the cation types of the ligand. And you must know whether this ligand act as monodentate, bidentate, or tridentate, and so on. So the idea about the charge of the ligand is denticity, and the exact metal ion charge is very important. Now we'll discuss how we can find out the EAN of these complexes. Let's take first example. We have scandium complex, and in which fluoride ion is a ligand. So you can see very carefully in this complex we have a coordination number is equal to 6, right? Because fluoride ion is act as a monodentate ligand, and potassium carry +1 charge and F carry a -1 charge. So first thing, you have to find out the correct oxidation state of the metal. Now here, this is my central metal ion. Let's consider this as X, okay? So I can write down now, +1 is the charge of potassium, and we have 3 potassium ion into 3, okay? Now plus, I have given X is the oxidation state of the metal ion, which you need to find out, and plus I can write down now, -1 is the charge on the ligand, okay? Now here we have 6 fluoride ligand is equal to 0. Why 0? Because total these complex has the 0 charge. I can say this complex is a neutral complex and hence equal to 0. So if I solve this, +3 plus X minus 6 will be equal to 0, and hence I can write down X is equal to +6 minus 3, and therefore we'll get X equal to +3. And this is the way, remember, this is the way you need to always find out the state of the metal ion. In this, we have scandium in a +3 state. Now afterward, directly you can now follow the EAN equation, and here the Z value for the scandium metal is equal to 21, and minus N, oxidation state, we have 3, and plus 2, we have 6 coordination number is equal to 6, and therefore now I can write down here become 18, now plus 12 is equal to 30. So 30 is the EAN of this complex. But if you remember the Sedgwick electronic theory, he suggested that the 3D series metal ion, so if I am having the 3D series metal ion will try to get electronic configuration of the krypton with atomic number is equal to 36. And if this follow this thing, we can say the complex is stable. Now you can realize, according to Sedgwick theory of electronic concept, this complex is not stable since it do not have the noble gas electronic configuration. I am moving again for the next complex. So first thing, you should know the coordination number, the oxidation state, and the whether the ligand acts as a modentate or bidentate, and what is the charge on the ligand. Now next we have a titanium complex. So a titanium S2O by 6, right? And we have +3 charge. Again, steps are same. In this complex, we have coordination number is equal to 6. Water H2O each act as a modentate ligand, and the H2O is do not have any charge, is a neutral ligand. Okay. Now again, I can find out the charge on the metal ion. I can write down the x for this metal ion. Now plus, as I told you, the ligand carry 0 charge. So 0 into 6 and equal to charge on this coordination sphere. We have +3 charge, and hence I can get x equal to +3. That means the complex it has a +3 oxidation state titanium. Okay. Now after that, you can directly find out the EAN, and you know Z for titanium is equal to 22. Charge is +3 on titanium, so -3, and +2 into 6, we have a 6 coordination number. And after that, we can now get this 19 plus 12 again is equal to now 31. So again, by Sedgwick, it does not have the krypton electronic configuration, right? And hence this complex cannot be the stable one. So in this same pattern, you have to find out the effective atomic number, and EAN can give suggestion whether this complex is stable or not. So let's move to the third complex. This is a vanadium complex, and AC is called acetyl acetonate ligand, and this ligand is actually a bidentate ligand. I hope that you know this. AC, remember that is always carry a -1 charge, and this ligand is always act as a bidentate ligand. So I can now find out we have 3 bidentate ligand, and hence the coordination number of this complex will be equal to 6, right? And if we are having 3, so total complex having 0 charge, and therefore now I can say that vanadium should carry a +3 charge. Or else you can keep here simply x, right? And x we can write down plus, we have -1 charge on the ligand, we have 3 ligand, and the complex charge is 0, and therefore we will get x equal to +3. Well, this is the way you have to use the concept in order to find out the oxidation state. So again, we have EAN of this complex. We have scandium, titanium, vanadium. Vanadium is having Z value of 23. The oxidation state, which is N, is nothing but a 3 in the given complex. We have 2, and coordination number is equal to 6. Therefore, now I will get we have a 20, right? Plus we will get a 12, again equal to 32. And by Sedgwick, again this is not a stable complex. So the same process I am doing again and again. You might have realized that what are the things you require. Now here you look at the 4, okay, chromium complex. Chromium, we have here a Cn by 6, and charge is -4. Again I can do the same thing. A chromium, let's take X is the charge on the chromium. Now you know that cyanide is an anionic ligand, carry -1 charge, and here -1 into 6, right? And we have coordinate sphere charge -4, and therefore I can write down now X, right? X we have -6 equal to -4, and therefore X, this is equal to +2. So in this complex, chromium has +2 oxidation state, and therefore you can use now EAN rule. We have chromium equal to 24, am I right? Now here we have charge +2, then 2 into, again you will get 6, and therefore we have 22, right? 22 plus 12, and this is now become 34. Again by Sirvik, this is not a stable complex since it do not have a krypton electronic configuration, right? Now the same way you can able to find out the coordination number, the charge, and you can able to get finally the EAN. Now you look at this complex. In this complex, here we have Py. Py is nothing but the pyridine ligand, okay? And pyridine ligand is a moderated ligand and does not carry any charge, is a neutral. So if I find out the charge, you will realize that this is my neutral ligand, and outside the coordination sphere counter ion is Br2, and therefore this manganese should have +2 charge, right? Now once you finalize the oxidation state, directly use the EAN concept. Coordination number is equal to 6. Pyridine is moderated ligand, and therefore now I can write down here Z, manganese Z value is 25 minus 2 plus 2 into 6. Again you will get the EAN of the complex. Now here in this complex, this EAN is actually ethylene diamine, and this is a bidentate ligand, and it is a neutral, does not carry any charge. So in this complex, again I can say that this complex has coordination number 6 because EAN equal to 3, and since EAN does not have any charge, now we can find out the oxidation state. Oxidation state will be now again a +2. Now same thing, again use the same rule, you will get the EAN. Then next we have oxidation ligand. Here OX is called oxalato ligand, right? And it is always carry -2 charge, and this is a bidentate nature, right? So I can say we have OX3 means coordination number is equal to 6, right? Now if it is 6, again use the same rule X, you can do it X plus -2 into 3 equal to -3, then you will get the +3 the oxidation state, and hence you can use the again same rule in order to get the EAN concept. Now in the next, here if you look at, and if you use the rule again, you will come to know that the nickel oxidation state is actually a +4, right? Now fluorine is moderated ligand, is having -1 charge. Now you can use the EAN concept in order to get the effective atomic number. Now in the 9th complex, you can see this is the DMG ligand. DMG is actually called as a dimethyl glycine. And remember, when we remove one proton, and this DMG now carry a -1 charge, and this DMG is act as a bidentate ligand. So if I find out the coordination number in this complex, you will come to know that since DMG is a bidentate ligand, and hence the nickel coordination number should equal to 4, and the nickel charge will be equal to a +2. Coordination number is equal to 4, nickel charge +2, and the atomic number of nickel is 28. So we can do very easily 28 minus 2 plus 2 into 4. 4 is the coordination number. Similarly here, nitro, again nitro, you know that nitro is anionic ligand, right? So 6 nitro, and nitro is a monodentate ligand, and hence this complex has coordination number is equal to 6, and copper is having +2 oxidation state. So Z value of copper is 29 minus 2, okay, plus now we have 6 into 2, you will get the ultimately the EAN value. Now here in this complex, as you know that amine ligand is act as a monodentate ligand and is a neutral ligand. Therefore this complex has this tetraamine zinc complex has coordination number is equal to 4. Zinc has a +2 charge. Now again you can do the same thing. Z value of zinc is 30 minus 2 and +2 into 4, and so on and so forth. Now here if you look up palladium complex, now palladium, you might have realized that in this complex, since ligand is a neutral ligand, the charge on a coordination sphere is +4, and hence if this is a neutral ligand, a charge on the coordination sphere is actually charged on the metal ion. So we have +4 palladium. You should know the Z value of palladium. If you have palladium metal, the Z value is equal to 46 for the palladium. And here if you take again platinum complex, we have coordination number 4. Cl minus is a monodentate ligand, and each Cl carry -1 charge, and hence in this complex a platinum will have a +2 charge. So I can write down here a platinum here having a Z value is equal to 78. Okay, platinum is value 78. Now the next complex and the last complex we have silver complex, and here the silver has coordination number is equal to 2. We can see amine 2, and here a silver carry a +1 charge, and the silver has atomic number is equal to 47, and hence directly we can use 47 minus 1 plus 2 into 2, you will get the ultimately EAN value. Now you might have realized that how I am doing the EAN calculation. As I told already, you need to know exact value of Z for the metal. You must know how to find out the oxidation state and what is the nature of the ligand, anionic, whether it's monodentate, bidentate, and so on. In addition to all this information, you must also know whether the ligand is giving 1 electron or the 2 electron. Okay, that concept is also very important, because if the ligand is bridge ligand, it may not give always a 2 electron. So for that I'm going to discuss one complex. This is a di-iron complex with carbonyl as a ligand. So please try to focus. This is an important complex, Fe2CO9. This is the complex, and I'm writing the structure of this. Iron, we have 2 iron, and it carry iron bond, and here we have CO. Here again we have CO. This is CO, and this CO is actually this 3 CO called as a terminal CO, and again we have here CO, bridge CO. Here I am writing for your understanding. Here we have, here again we have a CO. Okay, so finally you must know this CO is actually called as the terminal CO. Remember, this is called as a terminal CO, and this CO and this CO is called as a bridge CO. Okay, again remember, when we have bridge CO, I can write down here CO in bracket bridge. When we have bridge CO, each CO ligand will give the 1 electron to that metal, and if you have a CO, a terminal CO, that will give the 2 electron. So suppose this is my complex. Now I need to find out the EAN. Now how I can proceed very easily? Now I can proceed. Let's say I am focusing on this part of the iron. We can able to find out as a whole. Now I am doing this only part, iron. So iron, you know that iron total electron, right? If I take iron as a metal, now we have 3D and 4S system, and now we have 3D6 and 4S2. Total we have 8 electron. Now I can write down very easily. So iron, we can see that we have 26 electron. Okay, remember we have 26 electron. Because here all the electron now from S will go to the D, because CO is strong field ligand. That part we discuss in valence bond theory. Now here, if you look at this iron has the 3 CO terminal, 1, 2, 3, and 1, 2, 3 are terminal CO. As I told, each CO will give the 2 ligand. Now if I write down here, I am having 3 into CO are terminal CO, and hence 2, 4, 6. I have 6 electron here. Okay, I have 6 electron. Now what left? Here we have 3 bridge. 1, 2, 3 bridge. So I have 3 bridge. So I can write down here CO bridge. Now this will be having 1, 2, 3. So 3 bits means 3 electron. Now afterward you might realize this is the metal bond. So for each metal I will be having 1 electron. So I'm having iron bond. So this will give the 1 electron. So if I calculate total electron in this iron center, I will be having, you can see 26, and this is 4. This will become 30, and we will be having 36. So this center will have 36 electron, and this is nothing but a krypton atomic number. And this is the way you need to find out exactly what I'm trying to tell, that you should know the how many electrons are given by that ligand and what are the number of terminal and bridge ligands are there, because this is a very important aspect. I hope that you like this video. If you have any question, please give me comment. Be in touch. Thanks for watching. Signing out.